Hello, physicists. Today we're going to have a look at the astronomy questions from the 2018 Higher Physics paper. So without any further ado, here we go. Question number 5. Hubble's law states that the universe is expanding. The expanding universe is one piece of evidence that supports the Big Bang theory. State one other piece of evidence that supports the Big Bang theory. So there are a number of pieces of evidence, Hubble's law being one of them, to show that the universe is expanding and therefore probably came from an initial singular point. Other pieces of evidence: the existence of cosmic microwave background radiation. This is this radiation that permeates evenly throughout all of space. And it indicates that the universe had probably all started in the same place. Olber's paradox. What that means is if the universe wasn't expanding and everything in the universe had been where it was for the whole time, the sky would appear white and not black. Because over time, more and more stars become visible. That indicates that the universe is expanding. And the abundance of light elements, hydrogen and helium, compared to heavier elements. The smaller elements were formed first after the Big Bang, and then over time larger elements formed as these smaller elements combined together in fusion reactions in stars. If the universe hadn't formed in the Big Bang, then there would likely not be an abundance of small elements, but would in fact be an even distribution of elements. B. A student plots some of the original data from the 1929 paper by Edwin Hubble and adds a line in order to determine the value of Hubble's constant HO. So we can see here the line on his graph, which is a little bit dodgy looking at it. When we're drawing a line of best fit, we want a reasonably even distribution of points above and below the line, and clearly here there are far more points below the line than above the line. However, we'll come back to that. The student calculates the gradient of their line and obtains a value for Hubble's constant of 2.0 times 10 to the power of minus 7 seconds to the power of minus 1. The age of the universe can be calculated using the relationship age of the universe equals 1 over Hubble's constant. Calculate the age of the universe in years obtained when using the student's value for Hubble's constant. So we just take that formula, we stick the student's value in, and we get a time of 5 times 10 to the power of 16 seconds. The question asks us to calculate the age in years though, so we need to convert that into years. So if we divide that by 60, we'll get the value in minutes. Divide it by 60 again, and that'll give us a value in hours. Divide it by 24, that'll give us a value in days. And divide it by 365 and a quarter, and that'll give us a value in years. And that gives us 1.6 times 10 to the power of 9 years, or 1.6 billion years. The current estimate for the age of the universe is 13.8 times 10 to the power of 9 years. State why the value obtained in B part 1 is different from the current estimate of the age of the universe. Well, go back to the graph that the student drew. And as I mentioned, it's quite clear that that line of best fit does not best fit the data. Really, the line should be something a little bit more like that, less steep, so that there is a more even spread of data above and below the line, and that line fits through the middle of the data, the average of the data. So the reason that the value obtained was not particularly good was that the student's line of best fit was incorrect. It was too steep. Suggest a change that the student could make to their graph to obtain a value closer to the current estimate for the age of the universe. Well, This is a little bit of a trivial question, but it would probably help if they drew the correct line of best fit. C. It has been discovered that the rate of expansion of the universe is increasing. State what physicists think is responsible for this increase. Well, somehow the universe is expanding, increasing in rate. Common sense would make us think that the universe should slow down and eventually run out of energy and then compress in on itself. So the current observations seem to be going against common sense. That would indicate that there is some other form of invisible energy causing the universe to expand. And that invisible energy is known as dark energy. Number 10. This question actually straddles the waves and astronomy parts of the course. In a laboratory experiment, light from a hydrogen discharge lamp is used to produce a line emission spectrum. The line spectrum for hydrogen has 4 lines in the visible region as shown. The production of the line spectrum can be explained using the Bohr model of the atom. State 2 features of the Bohr model of the atom. Well, there's quite a lot of things we could say here. We've got a central positively charged nucleus with negative electrons existing in energy levels around it. We could say that the electrons can move to a higher energy level by absorbing the correct amount of energy, or indeed can drop to a lower energy level by emitting a particular amount of energy. Or we could say that each line on a spectra is produced when an electron moves from one energy level to another. These are all valid answers to this question. Some of the energy levels of the hydrogen atom are shown. One of the spectral lines is due to the electron transition from E3 to E1. Determine the frequency of the photon emitted when an electron makes this transition. So going from E3 to E1 is that one there. So it's dropping from minus 1.36 times 10 to the power of minus 19 joules to 5.45 times 10 to the power of minus 19 joules. So the energy given off emits a photon of frequency f. So the energy of that photon is Planck's constant multiplied by its frequency. The energy is the difference between these two energy levels. And Planck's constant we get from our data sheet on the inside cover of the exam, 6.63 times 10 to the power of minus 34. So frequency is the difference between these two energies divided by Planck's constant, which gives a value of 6.17 times 10 to the power of 14 hertz. C. In the laboratory, a line in the hydrogen spectrum is observed at a wavelength of 656 nanometers. When the spectrum of light from a distant galaxy is viewed, this hydrogen line is now observed at a wavelength of 661 nanometers. Determine the recession velocity of the distant galaxy. So, the recession velocity. We need to first work out the value for the redshift of this galaxy. And the value of redshift, Z, is equal to the ratio of the change in wavelength divided by the rest wavelength. So we put our numbers from the formula into there, 661 being the observed wavelength, 656 being the rest wavelength. And that gives us a value for the redshift of 7.6219 and so on times 10 to the power of minus 3. This number is a very, very long number. Please don't round this number at this point in the question. Keep it in full in your calculator, because you need that number again in the next part of the question, where we work out the recessional speed. So maintain that number in your calculator, and then you can't end up with the wrong answer by rounding it incorrectly as you go through. So redshift is equal to the speed of the galaxy divided by the speed of light. So that redshift value that we just talked about there equals the speed of the galaxy divided by 3 times 10 to the power of 8. So the recessional speed of the galaxy is going to be that redshift value multiplied by 3 times 10 to the power of 8, which is that 2.29 times 10 to the power of minus 6 meters per second. And that, folks, are the astronomy questions from the 2018 Higher Physics paper. I hope that was helpful, and I'll talk to you again sometime soon. Bye-bye.